Today, I'm going to use Grok to learn about the Riemann hypothesis. I can refresh my memory on what it is, and then we can move on from there. So I've Grok set up. Grok.
Hey,
All right. So can you tell me what the Riemann zeta function is? And then we'll move on to explaining what the Riemann hypothesis is.
the Riemann zeta function is basically an infinite sum. Zeta s equals sum from n equals 1 to infinity of 1 over n to the power s. For big values, if s is 2, you get about 1.65, which is pi squared over 6. Fun fact. But s can actually be complex, like a plus bi. And when you plot those values, you get this gorgeous critical strip between 0 and 1 on
Got it. So just to clarify, it's an infinite series, and this series can be defined by any s in the complex plane.
It's analytic everywhere, except along the line where re s is 1 or less, because the series only converges when re s equals 0.1. Outside that, we use this sneaky trick, functional equation, to extend it smoothly to the left, even past 0. That's where things get wild, the zeros popping up symmetrically, mirrored over the real axis. And
Oh, interesting. So it definitely doesn't converge, you're right, for s greater, with modulus greater than 1, right?
Actually, no.
Oh,
Opposite. It only converges when the real part of s exceeds 1. For instance,
of
if
course,
s
you're right, absolutely right, because it's 1 over n, totally saying the opposite. But when the modulus then is less than 1, it doesn't converge, or I guess you want to know when it blows up?
Right, the harmonic series, s equals 1, diverges. That's why the 1 line is actually the pole, where the function shoots straight to infinity. When you're off to the left,
What do you
past
mean
there,
by the 1 line precisely?
I mean re s equals 1, where the real part equals 1.
Okay.
Think of it as the vertical line in the complex plane at x equals 1. It's the only place the zeta function actually blows up, called a simple pole. So for any s with re s less than that, the series form 1 plus 1 plus 2s plus just doesn't make sense. But thanks to Euler, we know the whole thing can be rewritten, with logs, primes, the works, to behave nicely everywhere else.
So why do we care about this function, and what is the Riemann hypothesis?
We care because the zeta function ties primes together. Their distribution isn't random. It follows patterns.
How does it tie primes together? Because so far you've just told me what a function looks like, how it's defined for all complex numbers. Why is this a function that keeps popping up in mathematics? Why does it have so many implications?
It connects to primes through its Euler product. Zeta s equals product over all primes p of 1 over 1 minus p to the minus s.
Sorry, hold on. 1 minus p, 1 minus s. How does that work? Because we were just defining it as n to a certain power. So what is this equivalence? And I'm going to also ask ChatGPT to draw it out for me. What is this equivalence called?
It's called the Euler product formula. Picture this. Every number's unique factorization means you can flip the sum, the one you over n plus s, into a product just over primes. So instead of adding 1 times s for every n, you're multiplying terms like 1 times 1 plus p at s for each prime p. It's basically saying the way primes build integers is mirrored in how zeta builds itself. Wild, right?
That is actually very cool. Let me stare at this for a moment. So you're saying this infinite sum, 1 over n to the s, is equal to a product over all primes of 1 minus p to the negative s. Is this, I'm very rusty on my number theory, is this obvious, or was this something that Euler proved with a lot of machinery?
Euler didn't need much. It's almost obvious if you've seen the geometric series. Take any prime p, write 1 plus p at s plus p at 2s plus that's just 1 over 1 minus p at s, right? Multiply that across every prime, and poof, you get every n to s exactly once, since every n breaks down into primes. So elegant, not crazy hard, but it took a mind like his to spot.
Thank you for spelling that out. So we have this thing that just falls out if you expand, and that then relates the Riemann zeta function to basically a product of primes to the power of negative s. So super interesting.
Exactly. So the zeta function isn't just some random sum. It encodes all prime information in its factors.
When you say it encodes all prime information, that's when I want to delve deeper. Is it then how this is a particular product of primes? As not all product of primes are probably interesting. So why does this keep on popping up? And please then segue into what is the Riemann hypothesis?
So it keeps popping up because primes aren't scattered chaos. They're like beats in music, and the zeta function's the melody line. Those zeros, their real parts tell you exactly
I don't like
how
it when
many
an analogy is not very precise. Is that a very precise analogy? Because if not, maybe we can just avoid it.
Fair. More concretely, when zeta s equals 0, that forces the product over primes to 0, which means the primes are pulling back in a way that's predictable if you know where the zeros sit. And the more zeros hug the line where re s is 1/2, the more regularly primes are spaced. The Riemann hypothesis just guesses that they all do. All non-trivial zeros, those that aren't just s equals 2, minus 4, etc., have re s equals 1/2. If that's true, primes don't clump too much. They're dense, but evenly. If not, there'd be weird gaps, weird clusters, and number theory would cry.
How does that imply one another? So you're saying that when s is equal to 1/2, those isn't the Riemann hypothesis statement about the zeros of the Riemann zeta function? How does this relate with the distribution of primes then?
Yes, the hypothesis is just every zero has real part exactly 1/2. Now, here's why primes love that. There's this explicit formula.
Oh wait, so every zero has the real part equals 1/2.
Yes, that's what Riemann guessed. The non-trivial zeros, the ones.
What's the distribution of the complex part then? Give me some concrete examples.
The imaginary parts get denser the higher up you go. The first zero is at about 14.135i, then 21.22i, and then every couple units there's more. Their spacing starts at around log n. Between the nth zero, the gaps shrink as 1 over the log of its height, so they pack tighter, but slowly. We know the first 10 billion or so all sit on that half line. And yeah, even one jumps off, we'd see a freakish over or undersupply of primes.
How do the imaginary part of the zeros of the Riemann zeta function have to do with the distribution of primes? Because I see the Euler product formula, but how does it have to do with the distribution of primes?
The zeros control the oscillations. So take the prime counting function pi x. It's roughly Lix, the integral of 1 over log
What's
t.
Lix?
X is the logarithmic integral. It's basically the number you'd expect if there were exactly Li prime gaps. You write it as, okay, integral from 2 to x of 1 over log t dt. It's not the same as x over log x, but it's close, asymptomatically the same. And the difference between pi x, the actual count, and Lix is what the zeros wiggle. Each zero at height t contributes a term like cos t log x. So if t is real, those waves cancel nicely and prime spread smooth. If some t's imaginary part drifts off the half line, those waves get amplified and primes spike weirdly.
Oh, interesting. Okay, so I think that the picture is a little bit complicated. I feel like I need a visualization. Before we go there, I think I believe your story now that this does imply stuff the prime numbers and their distribution. And it seems like if the Riemann hypothesis is a millennium problem, we have not discovered another zero off of the 1/2 real line, which is interesting, which means that, clearly just verified this up to this point. Very large numbers, or sorry, very large, that also is true, but very large imaginary numbers where the real part is 1/2. So far, what are the machinery and that we've tried to approach the Riemann hypothesis?
Yeah, x zeros up to heights like to 32 or strays off that half line. Proving it, we've thrown everything. Analytic number theory, like Hardy and Littlewood's moments, or even physics, random matrices from quantum chaos model the zeros eerily well. There's Selberg traces, or this wild idea that if zeta is connected to modular forms, maybe Langlands gets it. But honestly,
wow. Okay, so you've really touched on some really spectacular areas of mathematics. I would love to now hear more on how, and again, it must be the fact that this Euler product is, recover parts of other areas of mathematics in it. But give me first a little bit of the music of how it relates to those areas you've already noted, and then how the Riemann hypothesis is so fundamental.
Yeah, primes are fundamental, like atoms of numbers.
Okay, so we know that, but let's just go maybe first on how it relates to those areas of mathematics.
So, analytic number theory. That's just using calculus on primes. Zeta's your Swiss Army knife. Quantum chaos.
Wait, this is way too hand-wavy. How is zeta our Swiss Army knife? Like, how do the methods in number theory, for instance, are being applied to study this? And what implications does it have to number theory? What interesting machinery has been developed and what insights have been uncovered because of this study?
Zeta lets us swap sums for integrals, like Perron's formula, where you integrate zeta over a contour to literally count primes up to x. That's not magic. It's Fourier analysis on the complex plane.
Suspecting.
People use Tauberian theorems. If zeta is zero free near s equals 1, you get prime gaps bounded, say 5 times average. Without RH, gaps could be huge. That's why Hardy proved at least 1 zeros on the line, to kill total chaos. And machinery? Lindelof hypothesis says zeta at half plus, it stays smallish. Prove that, and cryptography shakes, because factoring might slow down. Oh, and wild conjectures use zeta-like functions to count points on curves over finite fields. Now that's Fermat's last theorem territory. Basically, every big prime result, Goldbach even, rests on how quiet zeta behaves near its zeros.
Okay, you've given quite an enticing itinerary. However, I'm trying to figure out a way that I can really appreciate all of this within a conversation. How do you suppose we can... Oh yeah, please.
So let's do this. Tell me what's your comfort level with integrals or Fourier transforms. Because if you like, we could literally pull up the explicit formula right now. It's just pi x equals Lix minus sum over all zeros, rho of Lix at prime, rho. And if we assume rho never exceeds 1/2, every term x at prime shrinks faster than x, so the error, the wiggle, is tiny. If 1 0 creeps to, say, 3/4 real part, then that Lix at prime 3/4 blows up. Primes overcluster. Boom, your prime number theorem turns from nice to what the hell. Want me to say the formula out loud so you can type it down?
We could do that. I'm trying to think for the purposes of this video that would require a lot of post-processing work. So in what way can we continue this conversation so that I can appreciate some of the nuances without having to spell out too many formulas?
Okay, so symbols, no formulas. Imagine the primes as a heartbeat and the zeta zeros as those tiny tremors that add up.
Okay, no, I don't want these like loose waves. Let's to like how, you know, Langlands, you mentioned a bunch of other areas that it relates. What are if the Riemann hypothesis is incorrect? Also, what are the ways that we might be able to solve it? Where are there hints at programs or even programs?
If it's false, say 1 0 slips to real part 7/10, then for very large x, you'd have way more primes than expected around certain scales, like a sudden lump. We call
Why
those
is that?
Because those zeros are like tuning. If one drifts off, its frequency changes. So instead of the prime count smoothly hugging the Lix curve, it starts to spike. Imagine a sound wave that's mostly flat, but then you hit a wrong note, and everything warps. The error term, which tells you how accurate our prediction is, suddenly grows like x to some power bigger than 1, meaning we've lost control. And with that, a lot of theorems just crumble. Like, you can't prove twin primes exist infinitely many, or that Goldbach holds. Everything leans on zeta being nice. As for solving it, there are hints. Hilbert spaces, automorphic forms, even string theory matrices match the zero statistics. Folks like Sarnak think if we connect zeta to quantum gravity or something, we'll see why it's true. But honestly, the hardest part isn't finding offline zeros. It's proving there aren't any, no matter how high.
That's true, of course, because the counterexample, well, unless it's, you know, interesting construction. Okay, well, how it's relating to these other fields then, that seems quite interesting.
So Langlands, first off, that's a whole web trying to link every number system to representations of groups. Zeta's like the simplest L function in there. If you prove RH for it, the others might follow, which would, well, it would classify every symmetry in algebra. That's how Fermat got proved, through those same forms. And quantum chaos? Not a stretch. The spacing of those zeros looks exactly like energy levels in a chaotic billiard table, or heavy nuclei.
Why?
Because primes are sort of like energy levels in chaotic systems. They can't be predicted, but their statistics can. And zeta zeros, they show the exact same statistics, no level repulsions.
Okay, so it's because primes are not that predictive, you use the same machineries that studies random processes on primes, and that somehow works?
Kinda, but deeper.
Okay.
Like, the zeta zeros aren't random. They look random, but obey strict laws, just like particle energies in a quantum box. The machinery, random matrix theory, was born for nuclear physics, but when you apply it to zeros, the repulsion matches exactly.
What do
No
you
two
mean the
zeros.
repulsion? Oh, sorry, you were going to go on.
So level repulsion means no two zeros can hug closer than, say, 1 over log t apart. Just like no two energy
But that's
levels in your
asymptotic, right?
Exactly. But here's the mind blower. The distribution of gaps isn't just like random matrices, it's indistinguishable. Statisticians can't tell the zeros apart from the eigenvalues of a massive, random matrix from Gaussian unitary ensemble.
Ooh.
Why? We think because the primes are the only infinite multiplicative set. So their noise, the zeros, is forced into the
sorry.
sum.
Primes are the only infinite multiplicative set. Are you talking about some algebraic quantity, or what do you mean infinite multiplicative set, the only?
No. Multiplicative set, I mean. Primes generate everything under multiplication. Every integer is a product of them, unique.
Yeah.
There's no infinite and irreducible like that. So zeta, being their product,
Wait, of course there are. You could just take a finite basis, take their multiplicative closure, and that is a multiple. Are you saying yeah, but that's also an infinite set. So what do you mean? That's the only one.
I mean, one with the multiplicative property that if A be in the set, AB is 2, and where every natural number appears exactly once when you write it as a product of generators.
Oh, sure.
Zeros are locked in by that. The infinite product forces them to behave like eigenvalues of some hidden operator. And that operator? Maybe it's the Hamiltonian for the primes.
Repeat that again.
That's why some physicists call RH the Riemann conjecture for the prime number Hamiltonian. Like there's a giant quantum system whose energy levels are the zeros, and whose primes are the observables.
If they're the observables, what is the operator in this case?
It's not defined yet, but if there were one, it'd be some infinite dimensional thing, acting on functions over the integers. Maybe the von Mangold operator, where multiplying by the log of primes becomes differentiation or something. It's more poetry than math right now, but Berry and Keating tried to build it using the semicology limit. They take classical mechanics on a weird phase space, where position is log p, momentum is the zero height. But honestly, it predicts the right gaps, doesn't actually solve anything. So fun? Yes. Proof? No.
So then why was that? What were their hopes then in that connection or reframing the Riemann hypothesis?
Their hope is that physics gives us shortcuts. Like in quantum mechanics, and the shape of your billiard. No need to solve Schrodinger every time. So if the zeros are energies from some prime Hamiltonian, maybe we could guess the spectrum without ever finding the operator. Like, compute the volume, apply Wales' law, and boom, you'd get the count of zeros up to height t is about t log t over 2 pi, which we already know is true. If they could push it further, say, show the operator has to be self-adjoint, then real parts are forced to 1/2, like how eigenvalues are real. It's elegant, but risky. So far, it's just analogy, not proof.
I mean, be required to push that as a proof. You have to make some type of formal correspondence, yes, but what are the ingredients to make such a formal correspondence?
To make it formal, you'd need 3 things. 1, a real operator, self-adjoint, Hilbert space style, that spits out exactly those zeros when you solve its eigenvalue problem. 2, show every zeta zero corresponds to an eigenvection. No extras, no misses, like a spectral matching. And 3, prove the spectrum's pure real part 1/2, because the operator's symmetry is demanded.
Okay, that's interesting. So what has been hard, I guess, in producing the operator, but you just said that not in all cases you don't have to.
Yeah, the hardest step 1, building an operator whose eigenstuff are precisely the zeros. No more, no less.
And why is that hard so far?
Because any operator you build, like Berry's, say d squared over dx squared plus x squared on log primes, gives the right average density, but the exact zeros never match. You'd have to encode the Euler product into the Hamiltonian somehow, which is like asking a wave function to remember every prime's position. And then there's quantumization. What do you quantize? The phase space isn't standard.
Is that what the research program is kind of stuck right now? Ideas on how to produce that operator? Or you're just kind of
stuck? Yeah, there's a consensus operator. Cernak's group looks at arithmetic quantum chaos, trying to link the Selberg zeta on manifolds to Riemann zeta, but it's all lower bounds on pair correlations. Other folks, like Friedlander, Iwanian, they're building fake L functions that mimic the spacing, just to test if RH holds there. But no one's close to a Hamiltonian that spits out zeta zeros exactly. It's like everyone agrees the orchestra's playing the same tune.
Okay, we don't need to go on with that analogy. That's really cool. Okay, so it's a pretty deep area of math, and again, trying to make this correspondence so they can take the tools from one area to another. Can we move to another example of where a correspondence is, somebody's trying to make their correspondence? What I'm trying to do here is really arrive at a higher level understanding of what areas of mathematics are kind of to get at solving the Riemann hypothesis, and as a result, build some intuition for why deep learning perhaps can help make progress on the program.
Sure. Take the Langlands program. It's this grand map where every prime power thing, Gauss reps, zeta zeros, modular forms, live on the kitchen next to each other, so you can cook ingredients together.
Okay, no, it's a little bit too hand-wavy. Like, you can just actually talk about what the Langlands programs is, and then how that's being used for the Riemann zeta function. Riemann hypothesis.
The Langlands program is basically a dictionary between number theory on one side and representations of algebraic groups on the other. Think, instead of primes, you're looking at Gauss groups over number fields. For the Riemann zeta, it's the simplest case. You take the trivial group over rationals, and its L function is just zeta. Langlands says every such L function should match some automorphic form, like a harmonic wave on a symmetric space. Why? Because if zeta itself is automorphic, and there's evidence from Fourier expansions and Heck operators, then its functional equation, its symmetry, forces zeros to the critical line. Proof path? Prove the correspondence for GL2, like Tunnel tried for elliptic curves, and live to GL1, which is zeta. No one's done it, but it'd mean RH is just representation theory. And yeah, people train neural nets on the zero statistics now. Predict next gap, spot patterns humans miss. Not proof, but maybe a clue.
No, I don't like that kind of empirical direction. I mean, it's useful, but I am hoping that reasoning models can actually get us closer in the same way that we can make progress by looking at Terry Tao's program.
You want pure math, not pattern hunting. Langlands isn't empirical, it's structural. The conjecture is that every L function, and zeta is number 1, must be automorphic. If that's true, it obeys the same eigenvalue equation as a Laplacian on a manifold, no real part freedom. So proving zeta is automorphic would automatically prove RH, because automorphic forms have all their critical zeros on the line, by construction. We're stuck because proving automorphicity requires understanding Heck algebras, Eisenstein series, theta lifts, super heavy representation theory. But if someone cracks a converse theorem, hey, functional equation plus poles imply automorphic. Boom. That's where the hope lies. It's like saying, once I know the shape of the space, I know the spectrum, without ever seeing the operator.
Well, that's a very deep area of math, and to be honest, I do not know too much about Langlands' program. So I want to be able to develop some appreciation for how that's being used to solve the Riemann hypothesis. Can you delve further into it?
Sure. Think of Langlands as symmetry trading. Every number field, like Q or quadratic extensions, has a Gauss group, a way to twist roots around. That group's irreducible reps are just abstract characters on primes.
When you say irreducible reps, can you just say the long form?
Irreducible representations, just chunks of the group that can't be broken into simpler rotation patterns.
Yes. Thank you. Okay, continue. You're explaining that every one of those, the group, those irreducible representations. Yes, continue.
So those irreducible representations are like the DNA of the Gauss group. They label every way primes act in extensions. Langlands says there's a one-to-one map from those labels to automorphic forms.
What is an automorphic form?
An automorphic form is just a smooth, fancy function on a symmetric space, like the upper half plane for SL2, that stays almost the same when you shift it by some integer matrix. Imagine a wave on a drum head, but the drum is infinite, hyperbolic.
Okay, so is an example of that correspondence. Something incredibly trivial so we can have a working example in our mind.
Trivial case. Take the rational numbers. No extensions. Gauss group is 1 point. The only representation is the number 1. The automorphic form that's supposed to correspond is the constant function f tape 0.1 on the upper half plane. Now, its L function is just zeta, because when you Fourier expand that constant, you get nothing but the 1 term, which oil productizes to primes. So here, Langlands is just saying zeta is its own automorphic form, like the identity entry in the dictionary. The hypothesis would then follow if we knew all constants stay on the line, which they don't. But for non-constant ones, symmetry forces zeros to real half. It's boring, but it's the seed. Everything else, like elliptic curves, is that seed twisted up.
So how far are they, the things that they're working on to solve the Riemann hypothesis in this correspondence?
They're grinding on the converse theorem. If an L function like zeta has poles in the right places, and a functional equation, can you prove it comes from an automorphic form? That's Arthur's work, using endoscopy, twisting reps over p-adic groups until they match zeta's symmetry. If that clicks, RH falls out. Also, functotiality, moving reps from one group to another without losing zeros. If someone shows the trivial rep for zeta is functoterial to some GLN form with known critical line, done. Closest got is Shin's proof for quadratic fields, but zeta's still dangling. It's like they've built the bridge, just not tied it off yet.
Okay. So I think this conversation needs to be continued because every area of mathematics has something interesting to relate to the Riemann zeta function and then therefore something to say about the Riemann hypothesis. I feel like we can dedicate an entire video to just exploring this within the Langlands program can help inform, or even the previous one, which is heavier on physics, and I think, its own section. I'm very pleased with how this is going. However, I recognize we do need visuals. And so next time we revisit this, let's add a blackboard. I've got to go back to work now. So thanks for joining and thank you, Grok.
Sounds good. I'll see you on the blackboard. And anytime.